Hi there and welcome from Ventura, California to today's webinar sponsored by Inside GNSS and Inside Unmanned Systems and Spirent Communications and hosted by WebAttract. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. Just a moment, we'll be introducing our panel of thought leaders as today's webinar is about hearing from these leading experts as they discuss positioning, navigation, and timing requirements for applications using both standalone GNSS and the many available augmentations, network, sensors, terrestrial, and more. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with all three panelists. Now, we've invited you, along with over 450 professionals from 50 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you will find today's webinar of value. Now, before we get started, Alan Cameron, Editor-in-Chief of Inside GNSS Magazine and PNT Editor for Unmanned Systems Magazine, would like to take just a moment to welcome you and to introduce our sponsor for today's session. Over to you, Alan.
Yes, indeed. Thank you, Lori, and welcome to everyone around the world. I see we have good attendance from, I don't know how many continents there are, but it seems evident there are 3 or 4 or perhaps even 5. Welcome to everyone. This webinar is sponsored thanks to Spirent Communication, and on behalf of Inside GNSS and Inside Unmanned Systems, I'd like to thank Spirent and introduce a spokesperson from Spirent, William Thornton, Product Marketer, Spirent Communications. William?
Thank you, Alan. We're delighted to be able to bring together these leading experts in the UAV positioning and navigation field. I've seen a few of our customers are in attendance, but for those of you who don't know Spirent, we are primarily a test and measurement product and service provider. We work with companies on 5G, wireless, security, cloud, but most relevant here on GNSS and additional PNT, so positioning, navigation, and timing technologies. Spirent has been a pioneer in this field since the mid-80s across a range of industries, but most importantly for today, we've been in a great and unique position to help transition knowledge from 20 years of defense UAVs into civilian applications. And as we go beyond line of sight, that knowledge becomes increasingly important. Today, we're lucky to have 3 expert speakers talking about precision in unmanned platforms, the threats they face, and what you can do to overcome these challenges. Whether you are developing, integrating, or using a positioning engine, I hope and expect that each of the presentations will provide insight that can help you lead the way in this high potential space. So again, thank you for joining us, and I'll hand you back to Alan.
Thank you, William. Once again, welcome. Today's webinar addresses the PNT, the positioning, navigation, and timing requirements as UAVs go beyond visual line of sight. And we have 3 expert panelists for you. I'll be introducing each one of them in turn as they speak. But here's a quick look at them. Akko Bleeker from the Netherlands, Adam Price from the UK, Howard Levin from Canada, myself based in Eugene, Oregon. We'll be taking your questions throughout the webinar, accepting your questions, and there will be a brief question session about midway through and then a much longer one at the end of the webinar. Before I introduce our first speaker, let's find out a little bit about our audience.
Absolutely. Coming up on the screen is that first poll. We'd like to hear from each of you. What is your primary interest or your primary concern in UAVs going beyond visual line of sight? We'd like for you to select one of the following choices: GNSS signal availability, GNSS accuracy, GNSS signal integrity, spoofing or jamming, or multipath. So, Alan, any thoughts here on those responses?
Well, signal integrity is the clear winner. That's not to say that that's a winning situation, but clearly everyone's concerned about spoofing and jamming and integrity. And, well, you're in the right place because our speakers will have something to say about that exact topic. Multipath and accuracy, which the two topics could be confounded a little bit, are clearly concerned. Signal availability, a bit less so, but still in the field. All right, well, let's get on with the content of the webinar. We're going to hear first from Akko Bleeker, who's a senior consultant at OFB Consult. Akko is an experienced senior consultant in the aviation and aerospace industry, skilled in aeronautics, configuration management, and aviation systems engineering, including the application of safety and reliability objectives. He has a professional background at Fokker Aircraft and 19 years at Rockwell Collins, primarily as Director of R&D in Europe. He now operates OFB Consult, analyzing system and mission objectives into required functions and performance targets, down to solution domain, recognizing conditional and constraining factors such as safety, power and weight budgets, and human factors, and above all, cost, or I should say, not the least, cost. Akko, please give us your presentation.
Thank you, Alan. Thank you very much. And talking about this subject, I think PNT really is a function that is part of a larger domain called Guidance, Navigation and Control. And Guidance, Navigation and Control, or GNC, is all about moving from where we are, our present position, and trying to get to the destination where we want to be, following a certain path, which then takes guidance and control to get there. And you will see that the variables, the most important variables, are then the cross-track distance. Are we on the desired path? Then obviously we have the track angle error. Are we in the right direction? Are we proceeding in the right direction? And then finally we have the distance to go, which I drew as a line here, but is actually the distance over the reference path, the along track distance, which obviously not just the distance, but also the speed and time attributes that we're going to derive from those. So this, in a nutshell, is the guidance, navigation and control system. And if we are going to make that a bit more formal, then we can show it as a closed-loop control system with at the top the reference trajectory, which is the string of intended positions, the estimation of the current position, which is obviously tied into the sensors. Then we have to generate the control error and find it and bring it down to the guidance and control functions so that it can act on the aircraft in order to influence its current state, and by that the sensors which pick it up and close the loop in that way. Let us think about the reference trajectory for a second. It starts out with a plan, which obviously includes a destination, and then maybe some interim positions like waypoints A, B, and C, and obviously there's a payload. The payload could be a cargo, or it could be a camera that you need to bring somewhere, or it could be another type of sensor or other device. Next, in terms of the reference trajectory, will be the aircraft and engine data that we are going to need in order to refine the plan to a more appropriate set of attributes that allow us to navigate. Very important are the constraints. There could be airspace restrictions or time restrictions. There could be winds and turbulence or other types of weather, and we have to make sure that they are properly included into what finally becomes the reference that we are going to navigate to. There shall be a navigation database. There are certain points in our navigation problem that we'll have to know, that we have to have attributes from, like certain waypoints, and jointly we then run a forward simulation whereby we exercise the plan, we respect the constraints, we use the aircraft and engine data, and we generate a reference trajectory. And this then is the series of positions and, straights and curved segments as a function of time, which then jointly describe the path that the aircraft has to fly. And this is a very important thing. If it is not right, then we will accurately go to the wrong location, which is obviously not the idea. To make it a bit more complex, we're navigating over the Earth, which is a sphere, a globe, and therefore you will have to express these coordinates in Earth-centered, Earth-fixed nomenclature, so that our present position, just like any other position, will receive an X, Y, Z and a time. So basically defining those in 4 dimensions. The constraints are similarly expressed in those same types of coordinates. And so that then is the basis for the reference trajectory, which is then in 4 dimensions, the path in space that we're going to have to fly. And obviously the guidance and control system develops the desired velocity vector from that and is able to then steer the aircraft along this reference trajectory. So then moving to current position, the reference trajectory, as we discussed, is going to have to be compared, if you will, with the current position in space. And we can then use a GNSS receiver, which is either a GPS or a Galileo, or maybe even a dual constellation machine. And we can decide to then augment that using a space-based augmentation system. And there are other types of augmentation, but this is one. And this set will actually produce a fix of where we are, so that we know at that particular instant where the aircraft is. We can then equate that to the reference trajectory, generate the control error, and basically offer that to the guidance and control system. This arrangement is typically sufficiently dependent for visual line of sight operations, and it is because the pilot sees the aircraft and provides redundancy in terms of visually estimating where it is. He is able to steer clear, and the requirements may actually be governed by the payload in terms of geotagging or timestamping or directing a LiDAR to a particular location. Now, if that is not sufficiently dependable, we can add a dead reckoner, so to say, and we can complement the fixer with the dead reckoning. And in dead reckoning, there's again 2 shades of gray, if you will. There's one that will use the velocity vector of the aircraft, like air data plus heading and so forth. But then there's also an inertial version where we measure the X, Y, Z accelerations in order to determine how the aircraft accelerates in the X and the Y direction. Obviously, we have to correct for attitude. There's a whole range of other corrections that we'll not dwell into, but this is the primary set of measurements that we have to make, and then we can successfully perform a dead reckoning, which really means that knowing where we start from, we can calculate where the airplane is at any particular time. And that then can be complemented with other sources of fixing, like a start tracker, for example, or we can have a range and azimuth measurement, such as a VOR, DME, or a TACAN in military airplanes. And in this case, we can create a level of dependability that will actually allow you to go beyond line of sight. Now that the pilot can no longer see the airplane, obviously we're going to depend more on this solution. So this is very much a diagram that you will see that will represent a beyond visual line of sight type of position determination system. Fixing is periodic, but it has a contained uncertainty, whereas that reckoning is continuous, but it has an increasing uncertainty. Since we calculate from where we started and then we integrate other dimensions in order to guess basically where we are. And you can clearly see that the 2 are complementary. So if we would fix and dead reckon in a combined way and make it a hybridized or synergistic solution, then we have dissimilarity in the fill modes, and we have a very robust approach. And we can immediately see that the application is going to set those requirements. If we do not want to go beyond visual line of sight, we may very well have sufficient from a GNSS complement. Whereas if we do go to beyond visual line of sight, we should look for continuity, integrity, and containment of any error, and obviously cost, not to forget. So looking at that, if we have a payload like a camera, then obviously it needs to be geotagged and timestamped. We may have designation functions. And in this case, the GNSS engine may be well enough in terms of precision and even in terms of integrity. And if there is a loss of data, then that is typically surmountable. However, if we steer the airplane depends on it. Now if we lose the GNSS engine for reasons of multipath or spoofing or anything, then we might lose control of the airplane, and that would be a much more serious situation. So in that case, we would try to use the combined set of fixing in that reckoning in order to make sure that this set can be critical to flight and that the vulnerabilities inherent to a GNSS are bridged, and that we use a complementary set to basically achieve the level of dependability that will get us through masking and interference and spoofing. So let us go to guidance and control, having talked about current position. Guidance and control is the next important function, since it has to be consistent with vehicle dynamics. It has to be consistent with the position determination frame rate and with the disturbance spectrum. Obviously, precision and resolution has to be consistent. Otherwise, we might know very precisely where we are, but we cannot get the aircraft to go there. And so these things are all, I should say, equally important almost, and they have to be properly integrated. This is an example of such an integrated system where we see the autopilot section, the flight guidance and control section in the center. We see the inertial triad here at right, and we see the air data section at the upper left corner with the power functions here at close to the connectors. So talking about error mechanisms, uncertainty and accuracy, the reference trajectory has to be correct, and it has to be valid. If it is not valid, then we are going to go to the wrong location. Then again, once it is on the aircraft, it has to be intact. It has to stay intact. So the database cannot lose integrity. We cannot corrupt the processing. Guidance and control. Cycle time is very important. Rounding and truncation is important in order to make sure that our control authority is in lockstep with what we should expect in terms of disturbance, but also what we expect from the demands of the reference trajectory. And then obviously the sensors, the current position, the GNSS has to be designed such as to be resilient against the main issues associated with such a high frequency machine, masking and interference, spoofing not to forget, and that might point to the need for redundancies to make sure that the error accumulation is kept inside acceptable boundaries. Now these three main areas are defined as the path definition error, the flight technical error, in other words, the ability to keep ourselves on the reference trajectory, and then the navigation system error, which is the key in the PNT discussion that we are treating here today. And jointly, they produce the total system error as a vehicle altogether. So, in summary, the reference trajectory is very important in directing the UAV. The sensors obviously have to determine the current state of affairs, and they provide intelligence to the payload. The guidance and control function resolve the guidance and control error, and they maintain the airplane airworthy. And then obviously there are corresponding errors and uncertainty contributions in actually all of the aspects that we have discussed. And we can clearly see that the preferred combination is very much mission dependent and to an extent aircraft dependent. But the mission and its environment is the one setting the yardstick for all of these applications. And with that, I should like to thank you, and back to Alan.
Thanks very much, Akko. For any questions that you may have, please send them in, and we'll turn to them in another 10 or 15 minutes or so in our first question session. But first, we're going to hear from Adam Price. Adam is Director of PNT Simulation at Spirent Communications. He holds a degree in Electronics and Communication Engineering and has postgraduate qualifications with Stanford University and the Chartered Institute of Marketing. He's worked in communication test, optical network, and wireless technology markets, and currently leads PNT Simulation at Spirent. Adam, the floor is yours.
Thank you, Alan. Thank you. Okay, right, I'm going to cover a little bit about the market we see and the applications and how they have the dependency on how that actually impacts the the performance of the PNT engine needed. And then we're going to go on to the typical sort of impairments that could be come across and how you can combat those and build that into test methodology. And then what are some of the considerations to go with that? I think there is no question that the market for UAVs is growing at a very exciting rate. Whatever market report we look at, and this is just one example from Market Research Futures, huge growth. This is talking about 76 billion by 2025, and it is global. And beyond visual line of sight is becoming more important within this sector. If that is the case, then there needs to be PNT resilience within the systems employed. And PNT resilience needs to protect from a number of areas which could inhibit the PNT engine. And this slide is just showing a number of those. Certainly, in our experience, interference, natural and intentional, is quite a clear threat. Multipath, which I'll talk about later, is something else which is quite significant and we need to think about. Well, the application space is wide, and depending on your particular application, you have different needs of precision, and the threats to that position vary as well, depending on that application. If I'm, for example, in mapping and survey, I do need high precision, and any vulnerability is going to impair that. If I'm in precision agriculture, I might have a wide open space to be able to navigate with my PNT system. However, often the antennas that are employed on some quite large systems can suffer from their own multipath impairments. If I'm into delivery, this example here, well, often I'm operating in quite dense urban environments, and my satellite signal visibility and multipath and interference all come into play. I still need relatively high precision. And if I'm in the inspection sector, well, you could be getting quite close to some interesting interference signals. If you're approaching things like power lines for inspection, you might be need big multi-antenna towers. You need to think about, what is this environment doing to my PNT engine? Occo talked about this navigation system. Well, certainly in commercial flight systems, there are some very good proven technologies that all come into play that feed into the positioning engine. As the system or the application requires us to simplify our systems, reduce weight from our systems, I think it's fair to say that GNSS, the influence of it, starts to become more weighted. We can't carry heavy, big inertial systems on our platforms. We use often on-chip type technology. Well, if we are going to rely more heavily on GNSS, we do need to think about these impairments. And certainly what we will see today is covering these four for sure. GNSS segment errors. Things sometimes can go wrong from the signals that we are receiving from space. We don't assume they are always right. Interference I've talked about, natural or intentional jamming. Spoofing, a lot of literature now about spoofing, and 5 years ago, more difficult to do. Now it's started to become more common. And then multipath, the other one that I just mentioned earlier. Think about these things and how they impact or could impact the PNT engine that you use on your UAV for your application. Just to reinforce something about this multipath impairment, well, this is a real 3D map of downtown Miami. The white signals you can see here are the simulated GNSS signals from space, which are in the area which this UAV under test, when we zoom in, would be able to see if there was no building obscuration. Actually, when you zoom in to what the UAV sees, it's seeing mostly these red lines. These red lines are multipath signals. This UAV in this simulation was actually navigating in a multipath dominated environment. The issue was that its PNT accuracy was impacted. So we think, how would we know as a UAV developer or PNT engine integrator that I'm mostly navigating, in this instance, off multipath with little line of sight? Now, the experienced ones among us will be able to detect this at a level. I think if you're just reading the PVT or the position that your engine gives you, don't assume that it is accurate and totally within the operational tolerances that you expect. So here's a couple of ways that you can think about what I could utilize for my PNT engine. And here's some really good, credible solutions here from a number of vendors. These are just examples. There are many good vendors out there. Well, all of these offer levels of interference monitoring and mitigation, multipath mitigation, mitigation against atmospherics and ionospherics, anti-spoof. They look at outliers in the pseudo range values that they were seeing from all the satellites and look for outliers. There are many features that you can utilize and look for flags for from your PNT engine. So please think about that when you are integrating these into your system. But it doesn't stop there. Most of the GNSS chipset providers, provide a GNSS, and some of them are fusing with inertial, but what they all have is these really great APIs where you can go deeper. You don't just have to use the flags that they sent that you can read and poll. You can actually go deeper and look at the data that the PNT engine is receiving, and you can use that to your advantage for quite low cost at the software layer within your system. So you don't have to pile in additional hardware and complexity. It's just about using more of the data that is provided to you. And here's an example here about using these APIs and thinking about it. Well, if you think about spoofing for a moment, well, rather than just accepting a spoofing flag, what you could do is you could read the navigation data that your PNT engine is seeing from the satellite signals that it sees through the number of channels that you have, and look to compare it. Most spoofers don't provide a full suite of navigation data. They're interested in trying to fool the system into locking onto their signal, but they can't easily sync with live sky and reproduce all of that navigation data. So you could just do a compare, look at all the channels and see, have I got outliers? You can also read the Doppler shift measurements. Spoofer is probably unlikely to be traveling as fast as a GNSS satellite and should have a different Doppler measurement coming from them. So that's just an example of spoofing, but again, multipath, you can read that and make decisions about when should I hold over to dead reckoning and inertial. The same for interference. Use the data that your PNT engine gives to you take it up to your software layer that you're integrating, and again, for relatively low cost, you can build these layers of resilience into your system. That concludes the first part of my presentation. I'm going to hand back to Alan for our Q&A.
Thank you, Adam. We'll be back with Adam in just a few minutes, but right now we're going to field a few questions from the audience. And the first one is for Akko. Excuse me. You indicate that aircraft and engine capabilities are a factor in constructing the reference trajectory. Could you please explain or elaborate on that a little further? And Laurie, if we can bring up the slide, I believe there was a constructing the reference trajectory slide that we'd like to look at.
Yes, absolutely.
Yes, thank you, Alan. The reference trajectory obviously has to be flown by the aircraft, and therefore it must match its performance. For example, turns are bank angle and ground speed dependent. A commercial aircraft may normally have limitations for passenger comfort, which then turns out to be a limitation in the bank angle. Likewise, ground speed depends on several performance factors. And to give an example, a large aircraft, a 737 class aircraft, has a turn diameter of in the order of 8 miles at cruising speeds, whereas if we take a small and more agile drone, then the turn diameter could be a few feet. And obviously we'll have to recognize that when constructing the reference trajectory. The other thing is, are we going to pass a turn change point overhead, or are we going to fly by it, so to say, making the curve inside the next straight segment? And then we will have to estimate what that means in terms of curve diameter and how we have to terminate the turn and rejoin the next straight segment. The same applies in the vertical for climb segments, the available climb performance, the lift drag properties, the load limitations. And so if we would define the reference trajectory without considering those aspects, then in the worst case, the airplane trying to fly it would start to build up error, and there would be no option to recover. And that is the main reason. It is to make sure that we have a reference trajectory that is totally reasonable and that will actually allow to be flown without error contributions. Alan?
Thank you, Akko. Another question for you. The title of one of your slides said uncertainty and accuracy. Could you elaborate on how those two concepts relate to each other?
Yeah,
and again,
thank you.
if we can see the slide, Laurie.
Sure.
Yeah, in fact, accuracy is always in relation to a known, let us say, beyond question reference. If we are on it, then we are okay. If we deviate, we call that error. But once we're on the airplane, we don't have such a reference. And in addition, the measurements that we make scatter. I mean, like watching a star and seeing the star twinkle, you could, fundamentally speaking, not decide where the star is until you sort of take a long-term look and average the twinkling. So if the scatter distribution is narrow, then we are inclined to believe that the error is low, even though we don't know for sure. Just like Adam just pointed out, we could have systematic errors induced by spoofers, for example. GNSS observations scatter. The scatter distribution now tells us the confidence that we may place, and that is why next integrity is very important. High integrity means that we have few hidden and unmonitored faults, and thus we may depend on it, and vice versa. So in airborne navigation accuracy, the three strongholds that we have is, first of all, the reference trajectory. Let us hope it is good and valid. The second thing is a narrow scatter distribution of all the sensors involved. And then finally, solution integrity. And the integrity is, in fact, one of the cornerstones of the whole solution, so that we can decide to use the data as it is meant to be. Thank you, Alan.
Thanks, Akko. Adam, just one question for you before we get back to your presentation. You alluded to the various PNT threats. What are the most common ones that you see in your experience, most common PNT threats?
I think the two that I mentioned, really, the ones that were most often asked to provide support in test on are certainly interference and multipath effects. I think there's been quite a lot of there's been quite a trend of how jamming is starting to come into play, where people are intentional jamming. A lot of literature around that. I think that is true. I think as urban environments are just becoming more dense with radio signals in general, and the spectrum filling up, that's not going to go away. The natural interference is something that we do need to continue to protect ourselves against, and that is certainly an ongoing an area for us.
Naturally. We'll return to Adam's presentation, but first, Lori, one more question for the audience.
Sure thing. And coming up on your screen is that next poll question. In what market segment does your primary interest or activity in UAVs lie? Again, selecting just one of the following: infrastructure, agriculture, transportation, defense and security, or other. Okay, looks like 11% infrastructure, 6% agriculture, 24% transportation, 30% defense and security, and 29% coming in with other. Alan, any thoughts here?
Interesting. Strong showing from the defense and security segment. That could be expected. I guess we missed the mark somehow in leaving such a wide open other category. I would hazard a guess that most of that is surveying and mapping, but there's no way to know. Unfortunately, we have a maximum of 5 options we can offer the audience. Transportation, of course, a very active sector, and infrastructure as well. Well, interesting. Let's return to Adam's presentation, and here, Adam, I would hazard a guess you're going to talk to us about testing.
Yes, thank you. Before I get there, I think I'd like to just give a couple of examples of some events that have happened in the real world. These are 2 examples of UAVs, one in the UK, one in Australia. Both of these examples, although slightly different applications, one's survey, one's broadcast, what we're seeing here is a UAV drone that took off, saw a GPS compass error, and then got to this point where there was loss of visual line of sight and then loss of control of the UAV. It was 25 pounds in weight, and it crashed into a roof of the house at this location. That was, the post-analysis was that was an interference event. This one here was at the MCG cricket ground in Australia, where the UAV took off, lost control here. In that event, the return to home function should kick in. It didn't, and the UAV continued to this location here before crashing. Again, this was an RFI interference event. Some speculation whether that was intentional or not. And on this next slide is, these things happen with, bigger aircraft. This actually was an interference event in Asia, and this was actually concluded to be interference from a tower with a DTV antenna on it, which had been damaged, creating harmonics in the GNSS band, and therefore GNSS interference, which then caused the problem. So, some examples there of where interference has come into play and really created a problem for operations. We often hear about the events where deliberate jamming takes place, but there is significant a number of events where that interference is non-intentional. So we need to think about building resilience into our platforms from the early design phase through to where we've actually got flight. Now, you can really get through some good software simulation, fuse that into the system modeling phase, which then goes into plugging into some of these real-world environments in simulation and seeing how the PNT engine really operates, and you can put simulated attacks into that PNT engine before you've really even built any hardware. Of course, by the time you get through to the hardware stage, you can go into chamber or controlled environment testing and then out to safe proving grounds. But it's about building that resilience in from the start of that system modeling phase and carrying that through, a bit like the V curves that we see in other market segments. Well, that can apply obviously here in the development of UAVs. And then when you are testing, thinking about, well, what do I test with? I can go outside and I can use the sky, or I could simulate, or I could record the live sky and play it back. But all of these have pros and cons. Live sky, very realistic, obviously, but you don't have any real control over it and you can't repeat it. If I simulate, well, I've got control, it's repeatable, controllable, and I know my trajectory, my truth. It's representative, not realistic. There's a pursuit to get this more and more realistic, but it's representative. And then record playback systems, well, I can repeat it. I can't control all of it. I don't know what the actual truth trajectory is easily, but it is realistic. So there's a number of things to think about here. One thing is for certain, let's say, how would you test your system against a leap second or a rollover event? It is a GNSS systematic event. How would you do that if you're not simulating? And then something as simple as time to first fix. Well, I don't want to do it once. Normally I want to verify over time to first fix many times in a repeatable, controllable way. Well, it's not repeatable easily if I'm just doing that in live sky, because those satellite signals and my environment is changing continuously. And then, the consideration. So, if you're going to start simulating, and that's something that obviously Spirent is very focused on. Well, think about this. The environment, how good is the environment that you're simulating within? Well, I showed you that earlier about downtown Miami. Can you use 3D world maps? We certainly recommend using real terrain data as much as possible, because that has an impact on the PNT system, quite obviously. Thinking about the quality of the simulated signals, the quality of the data if you're doing it in software. How fast can you simulate? What's your simulation rate and how low is my latency? It's pointless trying to simulate for example, a drone that is quite twitchy and moves pretty quick. The acceleration is pretty fast, but it's pointless having a simulation rate that's slower than the motion you're trying to simulate. And then the ease of use. You want to be able to plug it into other simulator environments just to expedite that whole design phase. It's very interesting when we speak to a lot of our customers, how many of them do not do the fundamental simulation tests. Time to first fix, how quickly can I acquire my signal, how well can I track it, if I lose it, how quick can I get it back, and then how accurate is my PNT solution for static vehicles or static receivers under test, and then ones that are moving in several axes. Those are pretty fundamental. And I think just doing those before we get into interference and multipath really improves resilience. And then the final one for me is to say, well, if you're mission planning and thinking about flying in a urban area, for example, well, being able to simulate also gives you a level of ability to kind of forecast the performance that you may expect at a particular time during the operation of your UAV beyond visual line of sight in a specific environment. So just something else to think about with the mission planning that you could undertake before operations. Alan, back to you.
Thanks, Adam. We'll have questions for Adam coming up, questions for all our panelists coming up. Meanwhile, we're going to go now to Howard Lavin, president of Micropilot, with 27 years of experience as owner, founder, and chief executive officer of the firm, which is a leader in professional autopilots for UAVs and drones, an ISO 9001 certified autopilot manufacturer that markets single board autopilots, enclosed autopilots, and a triple redundant autopilot. Micropilot offers a family of lightweight UAV autopilots that can fly fixed-wing, transitional, helicopter, and multi-rotor UAVs. The company also provides complementary products such as the Extender, SDK, and True Hardware-in-the-Loop 2. Micropilot autopilots have been purchased by more than 1,000 customers in 85 countries. Howard holds a master's degree in computer science from the University of Waterloo. Howard, please tell us about autopilots and simulation.
Thank you very much, Alan. It's a real pleasure to be here. So yes, I'm going to talk about a little bit about how Micropilot makes use of GNSS simulation as part of our product development process and production process as well. So as Alan mentioned, Micropilot makes a variety of different autopilots for drones and UAVs, from circuit board autopilots to enclosed autopilots to our triple redundant autopilot. We've been doing this for 27 years, and we've worked, actually now it's over 1,500 companies in 85 countries developing some sort of drone or UAV. And over that time, we've learned a lot of lessons. So the first question that you might ask is, why should we test more than we are right now? And I think the best answer to that is because we want better airspace. When we make our safety case, or better access to airspace, when we make our safety case to the regulators, we need to remember that they're used to seeing aerospace grade safety arguments and aerospace grade failure probabilities. And when we come with design processes that are more appropriate for, say, laser printers, they're going to be naturally nervous. And so if we just look at how we might want to use a UAV for a first responder in a perfect world where we had as much access to airspace as we wanted, likely what would happen is the UAV would take off at the same time as the first responder left for the accident scene. It would fly straight to the accident scene. It would arrive ahead of the responder and start providing a video to the dispatcher so that she could determine whether she dispatched the right people and the right equipment. It would provide information for the entire duration of the accident, and because of the high capability UAV, would provide very good video. Now, today, if you want to bring a drone to the along with a first responder, it has to travel to the accident site with them. Maybe they get stuck in traffic a little bit. When you get to the accident site, you have to set up. Then, yes, you're flying, and you can provide some data for, say, half an hour to 45 minutes, but then you have to land, change the battery, and keep repeating. And so, this lack of access to airspace, this inability to fly in the same way that occupied aircraft fly, means that the market is quite distorted right now. There's a lot of drones being driven around in the trunk of cars that really should be flying to their job site. So the next question is, what is reliable in terms of aerospace standards? And so when they're looking at the consequences of a failure, there are two things that you have to consider. One is the actual consequence, and the other is the type of vehicle. So for all types of vehicles, if you have a risk that is have low consequence across the board, regardless of the type of vehicle, the probability that's expected is 10 to the minus 3, or one failure per every 1,000 hours, or every 42 days. Now, I have a small plane. I like to fly. If you start looking at failures, a failure that could cause my small plane to crash, now the regulators want a probability of failure of 10 to the minus 6 per hour of operation. So this is one failure for every 1,000,000 hours, or one failure per every 114 years of continuous operation. So you can see that for low-risk failures, 1,000 hours, you can probably prove this just by collecting some data. But once you're getting to a failure rate of 10 to the minus 6, you can no longer prove this by just with data. And if you look at airliners and vehicles that have higher consequences when they crash, the probability that the regulators want is 10 to the minus 9. And that's one failure for every 1,000,000,000 hours of operation, or 114,000 years. Clearly, you can't do that with data collection. And just to note that this 10 to the minus 9 probability, while it does apply to airliners, it's also been mentioned as an appropriate failure probability in some proposed standards for larger UAVs flying over dense crowds of people. So, how do you, and the other thing to note is that this is what the aviation regulators are expecting to see. They're used to seeing this. They're used to people coming to them with documentation that shows that their failure probability is in the order of 10 to the minus 9 for individual failures. And so the question is, well, how do you prove that you can achieve this failure rate? And the answer is, well, it's a three-step process. One is you have to do a very thorough analysis of all the different ways that your product can fail. And then once you have that analysis for each failure that could result in serious consequences, you have to show what mitigations there are and show that the probability of the failure combined with the mitigation meets the target set by the regulator. And then finally, you have to collect a bunch of test data that shows that your mitigation actually works, that it does the job. So since the GNSS receiver is such an important part of any autopilot or any drone, I'm going to use that as an example of some of the ways you can show to regulators or collect the appropriate test data to show that you have the reliability that they expect. So this is a picture of the one of the GNSS simulators that we use. So this simulator, we can give it a position and an orientation and a time anywhere in the world, and any time past, present, or future. And this simulator will generate the RF outputs that the satellites would generate at that time and at that position. So an example of where we've used this is the GPS rollover event that happened a couple of years ago. So one of the counters that the GNSS satellites are broadcasting was about to reach its maximum value and revert back to 0. And about 6 months before that, we wanted to know, we wanted to make sure that this wasn't going to be a problem for us and our customers. And so using this simulator and a number of test processes we came up with, we were able to project 6 months forward into the future, run some simulations, and show that neither our autopilot software nor the software in the GNSS receiver we were using were going to experience any adverse effects. Another place where a GNSS simulator comes in handy is with multipathing. So multipathing occurs when the signal from a satellite does not take the nice straight path to the receiver, but instead bounces off something else. And when you start to experience a multipathing event, you get these sudden jumps in position. Now, the GNSS receiver will give you some indication that you're experiencing multipathing, but also you can see this by comparing your inertial navigation system to the output of your GNSS receiver. Suddenly, there'll be a big difference between the two. Now, in our software for Autopilot, we do a lot of work to recognize a multipathing event. We do a lot of work to try and mitigate it while it's happening, and then recognize when it's over and make our solutions converge again. Now, this is really hard to test in the real world. You can go a long time in your test program without experiencing a multipathing event. So it's much easier if you can generate these events in a controlled environment with a GNSS simulator, and then use that to prove out the operations of your algorithms. Another place we use GNSS simulation is part of our hardware-in-the-loop simulator. We have a hardware-in-the-loop simulator where we actually remove the individual sensors from our Autopilot circuit board, and we have specially designed hardware that mimics the electrical inputs that those sensors would generate to the Autopilot. So we can use this simulator in two configurations. In one configuration, we have one of the sensors we remove from the Autopilot is the GNSS receiver. And we'll have a block in our Simulink simulator that generates the same packets as the GNSS receiver. However, sometimes we want the receiver in the loop in the simulation. And so then what we do is we replace the block in Simulink that generates the GNSS packets, and instead we send the state information of the UAV to the GNSS simulator. So the position, the velocity, the orientation, and the time. Then the GNSS simulator will generate the RF that the satellites would generate for a UAV in that state, and then we output that into the antenna of the GNSS receiver. And now the GNSS receiver is part of our test. And there's a lot of different tests you can run with this. For example, sometimes we run month-long flights to make sure there are no cascading errors in our software or in the software in the GNSS receivers that we're using. And as you can imagine, to fly for a month would be pretty tricky, but in the simulator, that's quite straightforward. Another example is high-G catapult launches. Sometimes when a GNSS receiver gets outside of its design specifications, it can do strange things, and your Autopilot software needs to be prepared for this. And so with the GNSS simulator, you can simulate all sorts of corner cases like that and prove out your software. And so here's a picture of our GNSS simulator. On the left, Autopilot under test is in the middle, and our ground station software is on the right. Now, in production, GNSS simulation also has an important role. Our Autopilot includes a GNSS receiver, and we want to make sure that the GNSS receiver on all our Autopilots is working properly before we ship them to our customers. Now, we could just take that outside and test it under the open sky, but unfortunately, then we don't have a known signal strength, and so we couldn't be as precise on the signal-to-noise ratio we expect from a properly functioning Autopilot. So taking advantage or making use of a single channel or single satellite GNSS simulator gives us that known signal strength signal. So we just take the output of this and we connect it to the RF input on the GNSS receiver, and for every Autopilot, we know the signal strength of the satellite that we're supposed to be checking for. Now, when you get into designing a drone, you're taking a whole bunch of transmitters, everything electronic is a transmitter, and you're placing them very close to your GNSS receiver antenna. And so it's no wonder that sometimes there will be problems with interference. And again, you can try and resolve these interference problems under the open sky, but then you don't really know if you're making it better. Just because the signal-to-noise ratio you're reporting today is better than it was yesterday, that could be because of the changes or the improvements that you made, but it also could just be because the satellites are in a better position. So, being able to use a single-channel GNSS simulator with the signal into an anechoic chamber, this gives you a known signal strength. And so if you make an improvement, you know that if the signal-to-noise ratio is better, then you know that the improvement you made is really an improvement. And here's a picture of a small drone in an anechoic chamber. Now, the orientation of your drone also affects the signal strength. And so it's important to test your drone in a variety of different orientations. So if you rotate it through 360 degrees at a number of tilt angles, that's an important test. Again, because the antenna you're using has a reception pattern, and there can be obstructions on the drone itself. And finally, once you're in production, it's important that you check every drone before you ship it to your customers. And again, you can do this under the open air, but it's much better to do it in a controlled environment with an anechoic chamber and a known signal strength signal for the GNSS satellites. So this is how we use GNSS simulation at Micropilot and how we think that it can benefit our customers. And we believe that this is the sort of thing that the regulators are going to be looking for to allow you to prove the reliability of your system. So thank you very much, and back to you, Alan.
Howard, certainly getting approval from airspace regulators is a key consideration for all UAV manufacturers and users. It's a bit of an unknown, undefined, we should say, as yet area, and proving reliability, as you say, is key. For the benefit of our audience, we have a number of further resources here. You don't need to jot them down. Of course, you will get this presentation via email. You'll get the slides. But there are 2 white papers, 2 ebooks, and 1 simulator brochure, I should say, for your benefit there. Just scan them quickly, and then we'll go on to our third audience poll, please, Lori. Here we go.
Okay. Let's go ahead and bring that up on the screen. With what testing methodology do you have the least familiarity? Live sky simulation, record and playback. Looks like we have 27% live sky, 41% simulation, and 32% record and playback. Any observations here?
Well, I'm surprised to see that a significant number of people have the least familiarity with live sky. Would not have expected that. To be sure, we're talking about the importance of simulation here, and this is to the audience's benefit, since they have nearly half have the least familiarity there, and certainly it is I don't want to say advanced, but it is a higher level of testing than simply going out and flying in live sky. And of course, record and playback is another significant method that bears investigation. And as Adam pointed out, each method brings different aspects into play. We have a couple of questions for Adam coming up. Adam, as a UAV provider, for a UAV provider, what PNT threats should you test against during design?
I think again, I mentioned those fundamental tests. I think they are the baseline. The ability to have a repeatable environment, controlled environment, where you can do some of those simple basic things like, as I said, time to first fix, what's the sensitivity capability of my PNT GNSS receiver, do the simple tests of losing acquisition and then seeing how long it takes to get back. And if you're working with an inertial system, well, input to your Kalman filter, thinking about, well, when do I hand over to dead reckoning and when can I switch back? And I think some of those basic ones early on, and I think, as I mentioned, that you don't have to have all that in hardware. A number of these things can be done at the software leveling model. Your simulation can start at that software level. So it can be, and then it can be regression tested as much as you need. I think then going on beyond that, it then comes down to the specific use cases. So if you are working in those urban environments, you do want to be testing for multipath effects, and how representative of that can you make your test. The ones that Howard mentioned as well, I think just some of those basic systematic tests of that will happen at a point in the future around leap second and rollover, that needs to be done. I think with UAVs specifically, you at a point in time, your PNT simulator is going to need to get plugged into a UAV environmental simulator, where all the things and factors of how a UAV moves for your particular use case. You might have your own trajectory models, how they respond to the environment around them, all starts to come into play there. So I think starting off with the fundamentals, then it's down to the application space that you're operating in. Do I need to be worried about interference? Well, then test it early on, get some real representative interference signals that you can do in a controlled way, rather than just taking them out into live sky and hoping that you may come across them.
Thanks, Adam. A couple of questions for Howard. Howard, why is it important to use an anechoic chamber when testing a GNSS receiver with a single satellite receiver?
Thanks, Alan. Well, it's important because you're generating RF output. You're generating real GNSS satellites signals, and they could confuse or interfere with other receivers in nearby. And usually these simulators are a little more powerful than the satellites, and so it's mostly a safety consideration. But you shouldn't be put off by the fact that you have to use an anechoic chamber. They're not that expensive, depending on the size of your UAV, and at least the single channel simulators to me are quite affordable. Thanks, Alan.
Don't go away, Howard. We've got another one here for you. Do you need to test for different GNSS systems like GLONASS and Galileo, and let's throw in Beidou as well, in addition to GPS?
Yeah, certainly. And again, it depends on the receiver you're using and your target market. But you should also keep in mind that some of these GNSS systems, you can't receive them from where you are. And so, how do you validate that they're working properly, or that your software or your system works properly with them when you can't even receive the corrections from them? So I certainly think it's important to test multi constellations, and that also should factor into the choice of your GNSS simulator. You should make sure that, especially for the single channel simulator, that you can simulate all the constellations you might want to simulate. Thanks, Alan.
All righty. Question for you, Adam. Accurate environmental information needs to include microscale weather information, especially in complex terrain like urban landscapes where wind and turbulence may significantly affect UAS operations. Is this something that you can factor into simulation?
Yes, indeed. I think my previous answer touched on it a bit. We, from our perspective of simulation, we ensure that the simulation environment that is, well, the simulation engine that is provided has a simulation rate and has low latency to take those types of features into effect. As I mentioned earlier, when you're getting into, you bring down in scale some of the UAVs, and the jerk, the rate of acceleration and their movement can get quite twitchy, and then wind shear and things like the microclimate statement, very, very true. What we ensure is that our simulation engine can be fused into your models that you have for things like wind shear, for example, and you can provide that as a trajectory information into the simulation environment, and that can be done quite effectively. And during our overview at the start, we're used to working with things that move pretty fast and through fast rates of acceleration and deceleration and environmental weather type effects. That can be all brought into effect within the simulation environment that you need in this space. I hope that answers the question at a high level.
Yes, I think it does. Again, a question about another question about the capability of simulators. We've discussed multipath. How can other sources of error, such as satellite orbital errors, be simulated and mitigated, for that matter?
Yeah, I think on that one, if you know what you want to simulate, then we as a, sorry, my badge is bang. We as a simulation provider provide that capability. So if for example, you want to change inclination or the eccentricity, or you want to change ascension rates of the orbits and you know what they are, you can do that. If you want to use your own Rhinex or UMA files, for example, with known orbits, we can do that. I think that's okay if you know what you want to simulate. To answer the question about protection, well, again, there are a number of things that can be thought about there. If you're worried about certain satellites having bad orbits and how that can affect you, well, a lot of these PNT providers, as I mentioned in the presentation, they have some built-in functionality to help you with that. The ranging mitigation method, that can go quite a long way, because what that is doing actually is looking at a population of satellites and looking actively for outliers. You would think that if you've got a satellite in a bad orbit, well, the pseudo range data that's coming from that, or the measurement that is coming from that, you would start to see something strange happening there, which could be detected by the PNT engine that you're using. I think just then generally, without going into tons of the detail, looking at the highest level, well, use multi-constellation, use multi-frequency, look at the nav data. You'd hope that not all of them are going to be in bad orbits. At best, or you really hope that one of them isn't in the bad orbit. But if it does happen, look for the outlier. You'd hope as well from an operational perspective, by reading the nav data and the health bits, you need to eliminate that bad satellite if it is in a bad orbit. We could spend a long time talking about that, but at the highest level, that would be my answer.
Thanks, Adam. Oh, well, there's a gentleman in the audience who's obviously very interested in Galileo's new oncoming services, the OSNMA, the Operational Service Navigation Message Authentication, and the HAS, the high accuracy service. Alco, excuse me, do you think that either of these services, Galileo's OSNMA or HAS, could help in the case of beyond visual line of sight operations?
Well, thank you, Alan, and thank you for the question. Well, there's the two things. There's the message authentication, which really plays into the authenticity of the signal that you're processing. So I think that not really helps in terms of accuracy, but it does help in terms of dependability. It will provide an additional layer of resilience against malicious interferences in the sense of spoofers or other signals that do not have the original authentication of the service provider. If you look at the high accuracy service, on the contrary, that is a couple of measures that are taken in the RF domain, where the signal over noise improvement allows actually a better accuracy to be obtained. Now, once you have better accuracy, you will also be more successful in correlating an overdetermined solution to one with integrity, like in a RAIM scheme. So even though it is primarily meant to enhance the accuracy, I think it will also benefit integrity. So the message authentication is obviously a matter of dependability, improved dependability, whereas the high accuracy service is accuracy and to an extent integrity as well. Thank you, Alan.
And a variant of that same question for Adam, what about inclusion of these new signal wrinkles, if you could call them that, or new signal aspects, or actually new signals in simulation? How is Spirent, is Spirent working on this?
Yeah, I think Spirent always has to keep ahead of what is coming, and whether it is these Galileo ones, whether it comes from, or whether it's new GPS services, yes. So if any of the users are interested in simulating these types of new services, then yeah, please reach out to us, and we can support you on that.
All right. We're going to step slightly away from the topic of GNSS, but fully on the topic of positioning and navigation. And I'm going to throw this question open to all three panelists. If you'd like to jump in, we'll go Adam first, and then Oko and Howard, if you have anything to add. Someone wants to know, to what extent do the panelists feel that the proliferation of 5G will create opportunities to address some of the possible shortcomings of GNSS? Adam, I know that Spirent has perhaps not in your division, but Spirent has deep involvement in 5G. What can you tell us about its possible PNT capabilities?
Yeah, I think 5G has been talked about for quite a while in terms of its PNT capabilities. Many different sectors: indoor positioning, industrial positioning, its use for emergency services for indoor. I think what we are starting to see an effect come into the PNT space, because 5G has a need to be, I'd say, prevalent beyond the urban centre. And some of the ways that that is being overcome is by putting 5G and similar high bandwidth signals into space in low Earth orbit. So that is fusing, not fusing, that is igniting really business cases to be putting new services up in space much closer to the Earth. I think there's much debate about how good or bad those types of systems could be for a native positioning and timing solution without GNSS. Most LEO today needs GNSS to locate itself in orbit. So I don't think I'm on the page of these new signals usurping GNSS and PNT. I think there is definitely a growing potential, though, that if you have these new high bandwidth signals close to the Earth in space, there is potential for new types of augmentation and new services to be offered by many more providers. So I think I'd look out for how these signals could be complementary to my PNT system over time, rather than thinking that, well, I can use that instead of GNSS. I don't think GNSS is going anywhere personally. So yeah, that's certainly my opinion.
Akko or Howard, anything to add to that?
Well, thank you, Alan. Yes, if I may, I would actually look at 5G more in the domain of interference rather than a supplementary service. 5G frequency has not been fixated yet, as you know. There's been, in the beginning, there's been operations in the 1 gigahertz band, very close to GNSS. Over in Europe, I think we're looking at frequencies in the 3.5 gigahertz domain, and in the future there could be frequencies as high as 8 to 10 gigahertz. Especially if we're thinking of the lower frequencies, then they're quite close to GNSS, and we should be worried about sidebands. I think, as Adam said, in terms of services, I don't think the GNSS operation will be replaced anytime soon by something that could go over 5G. So I would be most concerned about interference. So I rather see it as a threat than as a benefit, if you like. Thank you.
And Akko, you mentioned the lower bands being a threat to GNSS. Are you alluding specifically to Ligado in the U.S.?
Well, I mean, yes, they're not so far away from one another. There's been a lot of dispute whether the sidebands really kick into the the aerospace domains, or whether it's a suspicion without real evidence. I tend to think that the threat is not so huge and not so real as some people have tried to say. If you look at the higher frequencies, like the 3.5 gigahertz, then it's an interference potential to the radio altimeters, which is not so hypothetical. But again, there's these two things that one can consider. It's both the RF domains and then the service domain. I think in terms of service, it's a bit far away to see how that could change anything in the current situation. But the interference issue is more a concern that I should have.
Yeah, as you say, there's quite a bit of debate on the whether the interference is significant enough or not, and whether the if it is significant, as many experts say that it is, what is this going to do to the installed base of GNSS receivers, which is quite wide, quite broad, and in many industries, and what is the cost of replacing or upgrading somehow?
You see, I tend to think that the multi-constellation solution is going to be quite resistant against interferences like from 5G. For a fact, if you look at multi-constellation, multi-frequency solutions, they're almost 400 megahertz apart. So then to have a simultaneous interference on both is not so probable. In other words, then obviously you have to have the signal strength in order to produce the interference. So I think the multi-constellation, multi-frequency solution is going to be quite resilient. However, if you look at the radio altimeter thing, that is a bit more vicious almost. But that's not GNSS, obviously. That is the landing of automatic pilot landing system. So I tend to think that the developments in GNSS are actually quite good. We're going to see GPS plus Galileo, potentially with another constellation like Beidou, and jointly over multi-frequency, they should be very resilient even against interference from 5G in the low frequency band.
Mm-hmm. And for those of you in our audience who are not familiar or not overly familiar with the Ligado controversy, I refer you to the Washington View columns in the magazine, and you can access those via the digital edition of Inside GNSS on the website. We've had prolonged coverage for many years, and our current Washington View columnist, Don Zoldi, has written about it in the most recent issue, and of course will continue to write about it, as it is a very live concern in the GNSS industry. Well, we've done it again. We've used up a perfectly good 1.5 hours of your time. I hope you found it to your great benefit. I'd like to thank all of our speakers, Akko, Adam, and Howard, and ask them each to give us a concluding comment or farewell in order of presentation. Akko?
Well, thank you very much, and thank you for the opportunity. I indeed, I concur with what you just said. I hope it's been meaningful and helpful. And if there is any question, it'll be directed to the proper persons in the event, in the webinar. And if, time permitting, we'll obviously come back to those. Thank you very much.
Thank you, Akko. Adam?
Yeah, thanks again, everyone, for listening. I hope it was informative. Any kind of PNT resilience questions you have, or problems that you currently see within your projects that you're working on, then yeah, please reach out to us. We're there to help, and hopefully can help you with any challenges that you are seeing right now. And I hope what we did present was informative. Thank you.
Thanks, Adam. Howard?
Well, it's a real pleasure to be here, and I want to thank you, Alan, for organizing this, and Spirent for making great simulators, and I hope everyone found this useful. Thanks.
Thanks again to all three of our panelists. Thanks again to Spirent Communications for making the webinar possible. Thanks to you, the audience, for attending. Without you, it does not happen. And thanks to our backroom organizers, Lori and Terry. For the last time, this is Alan Cameron at Inside GNSS saying farewell and have a good day. We'll see you in another webinar next month, coming up soon. Bye now.
Okay, and if I could just add, echo all of those thanks Alan issued, and as well, again, thanks for joining us, and we hope to see you on the next one. Bye for now.